Yeah, so this morning I'm going to talk to you about coronal Alfvenic waves, and basically what we've managed to learn about the Alfvenic waves and the corona from observations of CoMP mainly, and I guess give you some indication of the things we can also do with UCoMP as well. And at the end, I'm going to give a very brief introduction to a tool we've developed, which has been called CoMP for now, but want of a better name, which is a Python-based tool that we use to do the wave analysis. And then this afternoon, Raoul will give a practical session on it. So I'm going to start with basically like a very brief intro to waves, and then move on to a bit of wave theory, just to, I guess, give everybody an understanding of the waves that CoMP is actually seeing and UCoMP actually sees. From then, I'll discuss various wave properties we've been able to deduce with CoMP, and also talk about what we also see in SDO that matches the CoMP observations. I'll then talk about wave damping, which was again something that we observed with CoMP, and then at the end I will demo this CoMP package. So transverse waves have been seen everywhere in the corona, and that was firstly through CoMP. So Steve's paper back in 2007 showed that these waves were ubiquitous, and then they've since been seen in SDO. So here we have two views of those waves. On the left-hand panel, we have the SDO image. So this is just 171 angstroms, so in the EUV. And this is a polar region. And you can see sort of fine-scale structure above the limb. And hopefully, if the video quality is good enough, you can see this structure moving from side to side, swaying periodically. It's much easier to pick out in CoMP Doppler velocity, which is the movie on the right. So this is just Doppler velocity from a particular day, not the same day as the AA observations, but here you can see in this this Doppler movie where I've done a bit of filtering, or probably not much, just maybe subtracting the mean Doppler signal away from it. You can see that there's these periodic black and white signals that are propagating upwards from the limb out into the corona, basically. And both of these represent transverse or swaying motions. And so with SDO, and I think using CoMP, it's actually better to study these Alfvenic waves, but there's a rich opportunity to do it at the moment, and even more so with UCoMP. So before I go on to the theory, I'm just going to discuss sort of like an aspect of the corona that I believe is particularly important. So this is just a standard SDO 171 image of the corona, and you can see, let's see if I can get a laser pointer. Yep. So you can see here we have an active region, and from many observations and many people sort of focusing on active regions that active regions are finely structured. You have these coronal loops that you can see, they're bright, you can see they're relatively small strands. But what I feel is not appreciated is that the rest of the corona also contains fine structuring. So you can't see it so well in this image, but as soon as you apply a type of filtering to a 171 image, you see all this fine structure appear around the limb. So the plasma isn't homogeneous throughout the quiet sun and in coronal holes. It's very finely structured, much like the active regions. So you can see that basically anywhere around the limb. So it's highly inhomogeneous, perpendicular to the magnetic field. And this is important for understanding the type of waves that you see. And you see, well, from the SDO data at least, you see the fine structuring down to the smallest resolvable scales. So this is just a power spectra, spatial power spectra, and where the blue curve begins to drop off, that is roughly at the resolution limit of SDO. So we're seeing sort of structure in the spatial structure perpendicular to the magnetic field all the way down to the resolution limit. This doesn't mean that this is the finest scale structure there is, just this is what you would see if there was finer scale structure that's smeared out by SDO resolution. So it could go to even smaller scales. This is not just seen in the low corona or in the inner corona. You also see this all the way out to about 14 solar radii. So these are some results from Craig DeForest, and he was using stereo. And what you see here is basically I guess, the outer edge of the sun unwrapped. So it's azimuth along the bottom and height along the vertical axis of this. So the top panel shows, I guess, the traditional view that you see from stereo core 2. You can see the large scale features, the streamers, maybe the presence of coronal holes in there. But as soon as you apply some kind of filtering, you actually see that there's fine scale structure. And most of the field is almost radial at this point. So when you look in the bottom panel, you see that there's this fine scale structuring that's, it's inhomogeneous, perpendicular to the magnetic field, all the way out to 14 solar radii. So that fine scale structuring that you see in the low corona remains all the way out to sort of the alpha and critical zone, basically. So what does it mean if the corona is structured? Well, it has an impact on the waves that it supports. So if you pick up a textbook on MHD, then it will probably tell you there are 3 wave modes: slow, fast, and alpha. But as soon as you introduce, slow, fast, and alpha, that is in a homogeneous medium though, right? So there's no structuring perpendicular to the field. As soon as you introduce that perpendicular structuring, the plasma can support many types of wave modes. So there isn't, say, a single alpha mode anymore. There's various alpha modes that you can have. There's also various fast modes and various slow modes. So you're not just restricted to those 3 wave types. There's kind of a plethora that can exist. The traditional approach to modeling the inhomogeneous structure, mainly arising from the active region studies, is that the corona is composed of cylindrical flux tubes. I guess this is just because of what it appears like in images that people have taken this approach. And if you make this assumption that these waveguides are near cylindrical, for example, then you have a lot of modes that are based on the axis symmetry of the cylinder, or the behavior about the cylinder's axis. And the one that is periodic and swaying from side to side is called the kink mode. The sketch here just shows transverse displacement that you see in SDO clearly, and you infer from the Doppler velocities of CoMP that this fine scale structure is swaying. The kink mode has very particular properties, and the most important ones are that magnetic tension is the dominant restoring force of this mode. It propagates vorticity. It's highly incompressible and nearly dispersionless. So those of you that remember the MHD textbook, this sounds a lot like an alpha wave. And in fact, a good description of this kink mode is a surface alpha wave. So it can describe nicely in a surface alpha wave. So it's very much an Alfvenic mode. So things we're seeing with CoMP are Alfvenic in nature. You can categorize them as a kink if you really want to, but Alfvenic is a better phrase from my opinion. And the nice thing about the kink mode, or one of the nice things about the kink mode, is that the phase speed depends upon the magnetic field strength and the density in the short wavelength, in the long wavelength limit, sorry. And this makes it useful for seismology. So recently, I guess recently is fair to say, there's been a number of papers that have questioned the cylindrical flux tube approximation of the corona. And these have largely arisen from radiative MHD simulations. And one that has been talked about a lot, at least say within my group, is a recent paper by Anna Melnichenko, who showed that the Morton simulations could produce this very realistic looking corona. So it looks like it was filled with cylinders or cylindrical flux tubes. But as soon as you look in the perpendicular cross-section of any of these cylindrical loop-like structures, there's no compact isolated feature that makes up that structure. Okay, so, and this is seen in many other, or a number of other radiative simulations as well. There's nothing in the perpendicular cross-section that allows you to identify individual structures. This picture then of the kink mode that really is only suited to the cylinder doesn't really fit so well with this picture. However, the surface alpha mode description is fine still. All you need is inhomogeneity perpendicular to the magnetic field, and you have a surface alpha mode. So my preference is that these are surface alpha waves, or Alfvenic waves, if you want to reach out a bit more to the kink mode people. So the corona is full of surface alpha waves, I would say. And I don't want to get into nomenclature, but this is sort of the best description in my opinion. But kink modes behave more or less like alpha waves anyway, so the difference is very little in terms of understanding how these waves behave in the corona. Okay, so what I'm going to do now is move on to what we've been able to find out about these waves from the CoMP observations. So STO is nice. I mean, you can see the structures swaying. It's got better resolution than CoMP, spatial resolution, and you can make out the individual density and homogeneities that they're moving side to side. But it actually doesn't make it easy, or it's not easy to pull out the wave properties from the STO data. It's sort of a lot more laborious. However, here with these Doppler velocity time series, it makes it very straightforward to probe the Alfvenic waves. So CoMP is very useful in that aspect. If you look in closed field regions, such as this one in the bottom of the movie, so I've highlighted it by this red dashed line, you can see that this is a loop-like structure that exists somewhere in the quiet sun, maybe on the boundary of a coronal hole. You see waves propagating up from one point and waves propagating up from the other point. And if you extract along that arc and plot the Doppler velocity time distance diagram, you see that feature. You see these sort of herringbone pattern of waves propagating up from both foot points. You can't really see the waves returning, which I will discuss a reason why later. But you can see them propagating up into the corona and following the coronal loop. When you look in an open field region, you have something very different. You see the waves are predominantly unidirectional. So here I've just shown an open field region at the bottom. And along this slit, same Doppler velocity time distance diagram, you see that the waves are largely propagating outwards. There's very little evidence for returning waves. Okay, so the waves are mainly propagating out in the heliosphere, which is kind of what you expect. In theory, there should be some wave reflection in open field regions just because you have a gradient in Alfvén speed, but that reflected component might be small. There's potentially evidence for it in the CoMP data. I published this in a paper in 2015, but I have gone on to be more cautious about those results from the 2015 paper. Even though I think there is still a bit of a signal of the reflection, I don't believe we can measure it as well as I thought we could. Yeah. So from the Doppler velocity time series, you can produce power spectrum and look at how the energy or the power of these waves is distributed as a function of frequency. And I did this for various regions. So I focused on an active region, a coronal hole, and a quiescent sun. And I found that in these regions, the power spectra showed a recognizable trend. So the coronal hole power spectra turned out to be the flattest. So this had a spectral index of about -1. And this is very reminiscent of what's seen in the solar wind. So in the solar wind, they also see this -1 power spectra. In the quiescent region, you got a slightly steeper spectral index. And then when you got to the active regions, you found that you had the steepest spectral index. So I've still not discovered the reason behind this. It might be due to some aspect of turbulence. So you expect the power spectra to steepen as turbulence becomes more developed in features. And if you have closed loops, you might expect turbulence to develop, in the closed field, and maybe not in the coronal hole until, say, further out away from the sun. So that could be one explanation for these different power laws, but it might not be the only one. The spectral indices actually have a much broader distribution. So they go from sort of just below -1 to -2. And when you look at it compared to the intensity, you see the same pattern that suggested by those 3 individual cases that I picked out. You see that when you have active regions, you have a much steeper slope, and where in a more open field region, you see that the slopes are flatter. So this is just the limb of the sun straightened out here, and this is the angle corresponding to that. The other interesting feature that's present in the power spectra is this bump, around about 3 or 4 millihertz. Okay, so this appears in every single power spectra in the corona. Back in 2019, I did a study where I looked around the limb, and I also looked over 5 or 6 different dates across the solar cycle, and in sort of 95% of the coronal power spectra, so I did some averaging for this, but in 95% of the coronal power spectra that we looked at, this bump was present. So there's always enhanced power around about sort of 3 to 4 millihertz in these Alfvenic waves. The peak is very clear on that. So this is just me fitting the power spectra and showing you the location of that central peak after basically fitting the peak. So it's very sharply peaked around 4 millihertz. Although it's not clear yet what is the cause of this, it could be an indication that the waves are actually being driven by P modes. So the typical idea is that Alfvenic waves are driven by Alfvenic waves are driven by the shaking of the magnetic fields by convection. So the convection shake the magnetic fields in the photosphere, they propagate upwards into the corona. However, work by Paul Kelly and Marcel Goossens in 2008, and then has sort of been taken on by Paul and Elena Kamenko more recently, showed that if you have acoustic modes coming through magnetic flux tubes, they can mode convert to fast waves, which at the transition region then mode convert to Alfvenic waves. So there's this different pathway for Alfvenic wave energy to reach the corona, other than this foot point shaking. And what might you expect? Well, the P modes peak around 3 millihertz. So it could be that you have a lot of power coming from this mode conversion process at a similar frequency. I don't believe it's going to be exactly the same frequency, because you have the acoustic cutoff in work in the lower solar atmosphere, you have the ramp effect from inclined magnetic fields. All that could act to actually shift where the peak of this power spectrum is going to be. But this is one explanation for this enhancement that we see everywhere. And the fact it's so regular, it's everywhere in the corona, you see it all through the solar cycle, suggests that it must be something global that's driving these waves. It's not like a local effect. And P modes seem to be a good option for them. Yeah, and this is me just showing spectra for the different days that I studied, where I averaged the Doppler signal over the entire corona, and you can still see that peak there. You still see that peak is present. It doesn't disappear. So the corona is almost ringing out at this particular frequency. So I'm not going to spend too much time on this, but I'm just going to note that the waves are useful for seismology. So in 2000, these are just plots from Steve's paper back in 2009 to demonstrate this. He took a time distance diagram from along this loop here, which happens to be this time distance diagram, and he showed that if you do Fourier filtering on the Doppler velocity time distance diagram, then you get this two-dimensional power spectrum, which shows this very characteristic star shape. So it shows waves propagating upwards from the foot points to the top of the corona, and it also shows the presence of waves propagating backwards, down from the loop apex to the foot point as well. And if you do some masking in Fourier space, you can separate out those two signals. So if you can separate out these two signals, you can see these Alfvenic waves moving. You see them propagating up through the corona, and because they're so clear, you can use these signals to measure how fast they're propagating. I mentioned before that if you assume a kink wave or a surface Alfvenic wave, you get pretty much the same expression, but the propagation speed basically depends upon the magnetic field and the density. That's the only thing it relies upon. Fortunately, with CoMP and also with UCoMP, you're able to get an estimate for the density in the corona, and then it allows you to measure the magnetic field with these waves. So I believe Zihao is going to talk about this in more detail a bit later, so I'm not going to say any more. I don't want to sort of steal his thunder, but it's a useful thing we can do with these waves. I don't. Oh yes, that's something. So I'm going to move very briefly to what we see in SDO. So this is that same movie I showed before, a little bit bigger. And when you plot the time distance diagram for this, so say, example, taking a slit across the fine scale structure and plot the time distance diagram, it's kind of difficult to pick out the wave motions in it because these features are, quite faint and they're not moving that much. But we developed a technique that was able to trace the structures over time in the corona. And this colorful plot on the far right-hand side shows those traces of the individual fine scale structure in the corona. And you can see a little bit better that these things are moving side to side sort of periodically. And so you are able to pull out the wave information from the AA observations. Okay, let me see. And for sort of a sanity check, back in 2019, I wanted to see if the waves we observed with CoMP were were the same things we were seeing with AA. And the only way I was able to do this really was by comparing the shapes of the power spectra that these waves had. So one thing that I'm going to talk a little bit more about in a minute is that the Doppler velocity signal in the CoMP observations is reasonably small. So the RMS velocity fluctuations are kind of 0.5 kilometer per second to 1 kilometer per second. Whereas the waves we measure in SDO, they have amplitudes of, say, 15 to 25 kilometers per second. So, an order of magnitude greater at least. So there's this disparity between the wave amplitudes. So direct comparison is kind of not possible just by looking at individual waves. So the best way, or a way at least, is through the comparison of power spectra. So the black and the pink show CoMP power spectra from the coronal hole and the quiet sun, and the blue and the green power spectra show the corresponding power spectra of the waves from SDO. SDO has trouble picking up the low frequency end of the spectrum, which is why we see a bit of a divergence. But as we get to that peak, we see that power spectra peaks around 3 to 4 millihertz and begins to fall off at the same rate. There's a lot of noise in the SDO observations. It's not as easy to pull out enough wave samples to be able to do this efficiently. But you can see that the general trend is the same for the higher frequency part of the spectrum. So this gave me some confidence that, the two AA and CoMP are actually observing the same thing. Okay, yes. So I just mentioned this, the amplitudes are different for the SDO and CoMP. And we also have the non-thermal widths from CoMP as well. So there's a disparity between the Doppler velocities and the non-thermal widths, which are believed to represent alpha waves as well. And the non-thermal widths are slightly larger in CoMP than the velocity amplitudes we get from SDO. So there's a bit of a mismatch between these three measures of the waves. The Doppler shifts from CoMP are small. You've got SDO amplitudes in the middle, and you've got the non-thermal widths, which are slightly larger. But it turns out you can get all these three to line up if you take into account the fact that you are integrating over many structures. The coronal emission is optically thin, and you're integrating over many density inhomogeneities, all oscillating out of phase along the line of sight. We did this with we looked into this with a 3D numerical simulation. So this was some work by Weibau and Tom van Doorselaar, and I was part of the paper. We did a 3D MHD model of an open magnetic field where it had randomly distributed density inhomogeneities. So you can see a cross section here showing those density inhomogeneities. And basically we drove it with an amplitude that we see in SDO. So we drove the waves with an amplitude of 5 to, distributed between 5 and 25 kilometers per second. And as soon as you start integrating over a number of different structures, so here this is showing basically the number of simulations that we stacked behind each other before calculating the synthetic emission, you see that the Doppler velocity amplitude drops, right down basically to about 1 to 2 kilometers per second, which is roughly in line with what CoMP sees. I don't actually have the plot for non-thermal widths here, but you find that the non-thermal widths tend to increase. I don't know why it does that. Probably because, well, I guess I can have a good guess, just because of the way the you have lots of Doppler shifts out of the line of sight, which broadens the line profile more than you'd think. So you also have the opposite effect, that integrating over many structures broadens the line profile more than the underlying amplitudes. So you can marry up these three different measures of the waves between EUV and the infrared measurements.
Can I ask a question, Richard?
Sure.
Is there a sense of like number? You've got it by number. Do you have a sense of what that means in terms of resolution, like arc seconds?
So this was, I'm just going to work out. So each of these simulations is about 4 megameters across. And so you multiply that by the number of segments, and you get that's the depth you're integrating over, basically. So we took a number of these columns of simulations and just stacked them behind each other to, represent integrating through the corona. Does that make sense? Does that help?
Yeah. So that's like, I'm sorry, I'm trying to do megameters to arc seconds in my head. Is somebody faster than me? One of you. Anybody?
An arc second 725. 7 megameters.
What was that? 0.7 megameters is one of the elements.
1 arc second.
One arc second.
So it's about
Or about 5
or 6 arc seconds.
Okay. Okay. Thank you. And so it looks like your hockey puck sort of levels off then at about maybe 10 of your elements. Is that right?
Yeah, maybe. Yeah, maybe about 20 to 30.
Okay, thank you.
Yeah, I guess they just used more to show that there wasn't any further decrease, I guess. I don't know. There wasn't any take into account, say, drop off with intensity, as you move away from the point above the limb or anything like that. It was just stacking these elements behind each other. So maybe something slightly more sophisticated can be done. But yeah, I mean, this drop off happens pretty quickly. You don't need to integrate over many or much structure to really see this decrease in Doppler velocity.
And actually, I'm realizing you have numbers up there on the upper right too. Yeah. Okay.
Yeah, I think this is height above the limb. I think these numbers are. I think that's what this is supposed to represent. I think it was a gravitationally stratified model. It's less important. I think the real important bit is the fact it just drops off quite quickly as soon as you start integrating over, multiple structures.
Can I have a question? I'm sorry.
Yeah.
I'm sorry. I don't get that. Is it resolved then that by the waves appear different in SDO or CoMP? Can you?
Sorry, can you repeat the first part again?
I didn't understand the resolution of the difference in the two wave measurements. I'm sorry.
So in SDO, what you can do is you can measure a density inhomogeneity, and you can measure its movement from side to side. You can't measure that in CoMP. What you measure in CoMP is the integration through the entire corona, the Doppler signal integrated through the entire corona. And so you're in CoMP, you're integrating over many oscillating structures that are potentially out of phase. And as soon as you integrate over many out of phase oscillating structures, the velocity, the Doppler velocity amplitude you measure is going to just decrease, basically, because you have some features, oscillating in opposite directions from each other, and so that decreases the Doppler signal.
So then when you show the power spectra compared.
Yes.
And yes. So why in the so which one should we believe in the low frequency range then? What is?
So in SDO, it's difficult to track the fine scale features for a long period of time. That's just because they're dynamic. They fade a bit, and they might drop. The density might drop below the signal to noise, which means we can't track them for that much longer. And so we basically have less low frequency observations, and I believe it's more of an artifact in the SDO data, that low frequency tail, and the fact that it drops off. It's just an artifact of how we can measure them.
So you would start to believe the AI data starting the frequency when it aligns with CoMP, basically.
Yeah, that's kind of where I believe it.
Okay.
We see most of the waves around about 100 to 500 seconds. That's where the bulk of the distribution of the waves we see in SDO is, which aligns with where the two plots overlap basically. To get the AAA power spectrum, you have to scale by the number of events that you've seen. That's the way it works out, in the maths. And so, because the way we measure these features, we just can't see a lot of low frequency waves. It means that when we scale it by the number of waves at that frequency, it drops off. It's an artifact really.
Okay, thanks.
I have a quick question.
Oh, sorry.
Go ahead. In the colorful plot on the right,
Uh-huh.
is the length of time over which you're able to track something, is that also in part a line of sight effect? Because you've got structures oscillating along the same line of sight.
Yeah,
Is
it could
that-
be you have structures that overlap and cross each other, and then we'll probably stop tracking it at that point.
And you have confidence that when you have the line, you are tracking the same structure. Some level of confidence that that's coherent structure. You have line
Well,
of sight effects in any coronal images.
Yeah, we believe that, from looking at the movies, it seems like we're tracking coherent structures in most of the cases. There's going to be a few cases where I think that you have structures overlapping, and maybe one of these or a few of these colored lines are multiple structures joined together. But this is kind of a brute force statistical approach to try and measure these waves. It wasn't finessed. We didn't take individual structures. We take the time distance diagram and kind of brute force it to just build up statistics. And there will be the odd few examples in there, I think, that are not perfect, basically.
Can I just kind of follow up on Joan's point there? It seems to me that you're probably very sensitive as to where you draw this slit, right? If you kind of tilt it a little bit, do you find very different answers?
Well, we place the slit so that it's always perpendicular to the inhomogeneities.
Sure, but that's kind of subjective a little bit, right? You kind of need to, how do you determine that inhomogeneity? And it varies from frame to frame.
Well, I mean, if you when you watch that movie, you don't see these things going. I don't know if you can see me on camera. You don't see them moving, say 10 degrees either side. You only see a small periodic displacement. They're largely there. They're largely, I don't want to say static, because there is some movement and evolution, but they don't. It's not as if they're tilting massively from side to side. That this approximation doesn't hold.
Okay, thanks.
Does that make sense?
Richard?
Yeah.
Is it a true statement to say that in order to bring the AIA amplitudes down to CoMP has to be averaging, if the AIA is 5 to 25 kilometers per second and CoMP is 1, CoMP has to be averaging over between 5 squared and 25 squared loops. Now it goes to square root of the number, right? Or is that 90?
I don't quite understand, Steve. Sorry.
I'm saying CoMP is averaging over these out of phase oscillating features.
Yep.
It has to be a lot of them, I'm saying, between 5 square and 25 square.
Well, you can see from this plot
It seems like a lot of features that are, we're averaging over. And maybe that's true. It just seems like a lot.
so this drops down. So in this box, it's 5 to 7 megameters long. By the time you get to about, I don't know quite what this is, 30 lots of that box. So it's 150 megameters. You have to average through 150 megameters of corona. I don't think that's too much.
Okay. Yeah. So my calculation is not right. Thank you.
And I had two quick follow-ups. First of all, this velocity amplitude reduction, this is the Doppler, but in terms of the propagation speed that's used in calculating the magnetic field from the waves, does it have any impact on that?
We didn't test that in this case. I think there's another paper where they did a similar type simulation to measure how it affected the propagation speed. And I think they came to the conclusion that it didn't influence it too much. I mean, there will be some line of sight averaging still. I guess it depends upon the conditions of the region you're averaging over. If you're in a coronal hole, it might not make too much difference because the coronal holes, are homogeneous, even though they're finely structured. They look relatively homogeneous over a large region. Whereas if you were maybe integrating through an active region or something that had a very bright structure along the line of sight in one small localized location, then there might be a bigger impact on the propagation speeds.
That's an interesting point to consider, maybe get at with forward modeling. And the related question is, I'm just trying to understand the resolution issue. There's the resolution in the field of view. So if we have cosmos, we have a much higher spatial resolution, but then there's also the difference of the wavelengths that we're looking at in the UV and the infrared, which may impact the way it's weighting and averaging along the line of sight. Which of these resolutions are we talking about here? The line of sight resolution or the fact that you're integrating over fat pixels in a way?
I think this is probably a line of sight resolution problem. I think Hinode shows similar amplitudes, Doppler velocity amplitudes to CoMP, and that's a factor of 4-ish better spatial resolution. So I think fat pixels will make less of a won't change the results that much. I think it's more integration through the line of sight.
I don't mean to belabor these points, but I have a full more question. UCoMP has a slightly higher spatial resolution than CoMP. Should we expect to see a higher wave amplitude in UCoMP than CoMP slightly?
Potentially. I think that's the best I could say, potentially.
Okay.
You should look.
Sure. And you see how I was going to say something.
I haven't compared the absolute value, but I think they are quite similar, just around or less than 1.5 kilometers per second for both CoMP and UCoMP. But maybe there's some slightly larger amplitude in UCoMP, but I haven't looked into that.
But that's consistent with what Richard said about ice being higher resolution, but not really impacting these results. Maybe it doesn't make a difference.
Yep, that would seem. Okay, go ahead, Richard. Sorry to.
No, it's fine. Just take a. I think I'm running out of time, so I might skip over this part.
You've got about 20 minutes.
Yeah, I'll skip over this. So I'll say something very briefly. The inhomogeneity in the corona can affect wave damping, basically. So it turns out it's easier to damp waves when the plasma is inhomogeneous. There are various ways to do this. One of them is resonant absorption, which is a transfer of the swaying mode to a rotational mode. And that's what's shown in this simulation. If you have a density inhomogeneity, the sort of bulk Doppler velocity of the inhomogeneous plasma gets transferred to narrow regions, basically. And it's a transfer of energy from the swaying to the torsional motion. And then a sort of enhanced phase mixing can kick in this regime. And we see evidence of this in UCoMP, basically. But I won't, sorry, in CoMP, but I won't go over that point. I think I'll skip it to go into this CoMP pi thing. It seems I've only got a bit of time left. So CoMP pi is around because I wanted to learn Python, and rewriting an IDL code in Python is probably the best way to learn. Well, it's a way to learn a language. I thought it was a good way to do it. So I rewrote basically the IDL version of the wave tracking code in Python. Made some changes as well, that kind of thing. So the IDL version was initially developed by Steve and Christian Bethke, I believe, a long time ago. I got hold of a version and modified it myself, and I worked from my modified IDL version, and the split from that version was around 4 years ago. I'm not entirely sure which version ZHAO picked up when he was using it, but yeah, this Python version has been slowly made over the last 4 years, and I split from IDL about 4 years ago. So what I found is that the performance is generally similar. You know, we get very similar results from the Python version, which is, you know, it's good. That's what you want. But in my experience, the Python version enables easy interface with sort of many useful modern packages. So I believe it's much simpler to, you know, make use of GPU acceleration through Python. Very easy to get hold of machine learning frameworks in Python, like TensorFlow or PyTorch or something, and sort of plug them in with CoMP if you really wanted to. And you also get access to probabilistic programming tools, which these are the kind of things that don't exist really in IDL, or they're not at the same level. So there's a lot more out there in Python that can be used to enhance this. This CompPy package that I've been developing, it does the same things that the IDL version did. So what it does is it takes level 2 data of CoMP or UCoMP, and it does some initial processing of the level 2 data. It will do some de-jittering of the data, and then it goes on to find wave angles and measure propagation speeds. And there's also a few other little tools in there that I've developed. So I'm just going to step through.
Can I ask a question on
Yeah.
the de-jittering, is that manual? Do you have to do that manually, or is that automated?
There is some manual aspect to it. I'll touch upon it in the next slide. Yeah. So what the initial processing stage does is it, you know, reads in these level 2 dynamics files. It'll help to filter out the polarization from the wave data. That's the first stage. And this is kind of a plot of the different types of data. So you see in the polarization data, this just shows cadence, so the difference between the frames in the FITS files. And you see that when you take the polarization data, that's taken on much longer separations. And then in the wave data, you have a very solid 30-second cadence. So it's relatively easy to spot the wave data from the polarization data and just pull out the wave data that you're interested in just by looking at the time separation between the files. This is a much longer one. It's difficult to see the frame numbers here, which is why I did this plot, but you can see we have wave data, polarization data bookending the wave data. And CompPy will produce this plot. You can see where the wave data is. You can see if there are any missing frames in there. And what the initial processing part of this will interpolate over these missing frames. There's a limit on the number of frames we'll interpolate. You can vary that. It's possible to extend it. So you can interpolate over any number of frames if you feel comfortable doing it, but we limit it to 3, you know, a block of 3 missing frames is our limit for interpolation, only because we're doing a linear interpolation, and we expect that, well, that's kind of a lower limit that I like to stick with, basically. I don't want to do any more interpolation than that. If it meets a big data gap, it'll truncate the series and only read in so much data till that big data gap. Otherwise, it takes the data that it's found, does the interpolation where it needs to, and then saves all that in a FITS file, where we call that the process data, where we've created new frames to fill in any gaps. During the initial processing, I also define a mask, and this identifies pixels which I believe should be excluded for further analysis, basically. And the mask is useful because in other aspects, say creating the wave angles or doing the phase speed propagation, previously the routines used to just loop over the entire data set, and that was looping over through many pixels that were not of interest, and it delayed, or it just took longer to do. So defining a mask and saying which pixels we want to work with later saves time when it comes to the looping aspects of the code, basically. So we define a mask in this routine, and we also save that. I'm pretty sure that's the only thing the initial processing does, kind of sorting out these data files. The de-jittering stage, I thought I had a picture of the, maybe I'll put it somewhere else. So the de-jittering, part of this is manual. So I found when I've been de-jittering the comp data, what I've found is that it requires me to select a region where there is significant intensity gradients in the image. So what I do normally is I apply a Sobel filter, which is a directional gradient filter to the images, and I just pick by eye regions where there's this strong gradient intensity. Then I use the original intensity images in that region with this strong intensity gradient to do phased cross-correlation, which means transforming to Fourier space, looking for the peak of the cross-correlation signal in Fourier space, and then we can calculate sub-pixel offsets from that. But after the initial selection of this high contrast region, then it does the de-jittering by itself. So, there's sometimes there's a bit of playing around with selecting the right region, essentially. So it's not entirely manual, not entirely automated, sorry. I wish it was. I haven't thought of a good way to do it. And I know this is a conversation that Steve wanted to have at some point, is how to make this an automated process. So yeah, it definitely needs to be done. The de-jittering part of the code will just take the region that you supply, work out the offsets based on that, and then apply those to the full images, and then produce plots for the offsets. So this is for one particular day, showing the X and Y offsets in the comp data. You see, there's never very many, or typically I find if it's a good day's data set, there's maybe a 1 to 2 pixel drift over the course of time in one direction, and in another direction there's maybe a fluctuation about the original one. But generally the shifts are quite small on good days. And then it performs alignment of the data sets in intensity, Doppler velocity, and non-thermal widths, and does that in the Fourier domain because it's sort of more accurate and efficient to do it that way than in the image domain. So they're kind of, I guess, standard packages, standard techniques. The next is the measurement of wave angle. So the measurement of wave angle is possible because Alfvenic waves travel along the magnetic field. There's no oblique propagation of Alfvenic waves. So they're always going to follow the fields. They're always going to follow those density enhancements, that inhomogeneity, if they're surface Alfven waves. And what that means is if you look at how the wave propagates, and you look at, say, the coherence. So the coherence is just measuring how similar a reference pixel, in this case, how similar a reference pixel is to its neighboring pixels. So this just shows a coronal loop, and we've taken a reference pixel from within this center of this box, and we're comparing it to pixels in the box. And this is typically what you see as you go through the corona. You see these islands of coherence. They're always elongated along the magnetic field, and they're shorter perpendicular to the magnetic field. So being able to track the waves in this way is relatively straightforward. It's a bit computationally intensive. All you have to do is work your way through every pixel, using that as a reference pixel, and calculating the coherence over small neighborhoods, local neighborhoods.
Quick question, Richard. When you say similarity to another pixel, do you just mean similarity in Doppler shift?
Yes, sorry. Yes, this is working with Doppler data. So not working with the intensity. So you only see Alfven waves in Doppler. Because they're highly incompressible, there's no intensity perturbations associated with them. And there's no perturbations in non-thermal widths because, well, I don't really know why, but you can't see it in non-thermal widths. You can only see the Alfvenic waves in Doppler, the propagation of the signal. So yeah, you have to work with the Doppler data to make these measurements. So this is very similar to what Steve originally did in the IDL version. He came up with this method. I've tweaked it in various ways. I'm hoping I can share this notebook now. Can you all see the notebook? Or
yes.
see the screen? Right. So this is just like an interactive view of what's going on in that code. So here we have the Doppler data, and I've got a red cross here that marks the position. I've then got a local region around that position. It shows the coherence. I then apply a Gaussian filter to smooth it out, just to get rid of any noisy values which can occur in this box. And then what we do is we measure the direction of this coherence. And here I show the pixels that have a coherence of 0.5, and this red line shows the measured direction in this case. And this then defines the wave angle, which we define from the horizontal. So as I move around the corona, this might jump a bit. You can see that the coherence changes. You get coherent blobs. Some are small and fat, some are thin and elongated. But you see this signal sort of everywhere through the corona. Oops, that's me going off. It's a bit sensitive. So this is what the routine is doing. It's going through the entire data set, calculates the coherence, finding islands of coherent pixels, and then basically fitting a straight line through these, and then from the gradient of the straight line you can calculate the angle. So this is how the wave angle code works. And it does a reasonable job. You can compare it to the magnetic field direction that you infer from the Stokes Q and U. We were talking about this yesterday. And it matches very nicely. So this is from Steve's paper in 2009. One thing I'm interested in is whether we can use the magnetic angle you get from the Stokes parameters combined with the wave angle in some way to improve the estimates. Because you still see there's some scatter around these two values. And I'm wondering whether there is a way we can combine them, or if it's possible to combine them to improve it. I'm sure there'll be some way to make it work sensibly. But it's something that I think is maybe a next step in improving measurement of plane of sky angle by combining the two. And the reason I'm interested in that, I'll go through this quickly, is to measure the propagation speeds. And the reason we're interested in propagation speeds, one is just to find out what the Alfvén speed is in the corona. I mean, nobody really knows. There's lots of estimates from extrapolations and whatnot, but it's an unknown thing. So being able to map the Alfvén speed in the corona is a good thing to do, and then you can also use it for seismology. And the way we do the propagation speed calculation I already talked about really is we take time distance diagrams, we make those by using the wave angles and building tracks. So I can give a demo of that if that works. So this is a wave angle map I have here, and this black line shows a track. Let's move it so I can see it on the green. The red pixel is the reference pixel, and what we do is we work out from this reference pixel and build up tracks by following the wave angle direction. So this is just a small subsection of a wave angle map, and you can see that as we go through the corona, these tracks change. I could probably get it over a coronal loop where it looks a bit more like it's following the loop there. You see there's some strange tracks that get built, like this weird bent one here. So it's not perfect. There's some issues there. Whether improving wave angle measurements will help improve this, I don't know. It's something that needs to be improved. But a lot of the wave angle, a lot of these tracks are reasonably good. You get a lot of problems around coronal loops, though. So you build up this map. You then go to your Doppler velocity data, extract the Doppler velocity data along those tracks, and then you filter it. So this is just an example of that happening. So here I've got one of those tracks on a wave angle map. This is the Doppler velocity data that gets extracted along that track. We then filter it in Fourier space. And here it's also got a filter on around about 3.5 millihertz. So it's where we see that strong peak in the Alfvén waves. And then from that, we measure the propagation speed by using cross correlation, essentially. We take the central pixel and cross correlate it with the pixels above and below it. And that gives us a time lag between the signals. So we can estimate the time lag via the cross correlation. And then we just fit a straight line through those, through the estimated lags as a function of distance. The slope of that line then gives the propagation speed. We've made it reasonably robust, so you can see here some outliers. They don't particularly affect the value too much. So we've tried to make it robust to various outliers you can get, which normally happens towards the edges of the time distance diagrams, the filtered ones, just because of Fourier edge effects, basically. And this is the outward propagation, this is the inward propagation, and we can build up maps of these propagation speeds. I'm not sure I've got an example actually. No. So we don't. Yeah, so we build up these propagation speed maps. You can then go and use them for seismology, such as to measure the magnetic field. I also used it in an earlier paper to measure the outflow speed in a coronal hole. So because you have waves propagating with a flow, that propagation speed is enhanced. They're advected by the flow as well, whereas the waves propagating downwards, their speed was retarded by that flow. And so you have a speed difference, and you can use it to measure flows along the structure of interest. So I did this in a coronal hole. I'm not convinced the method is accurate enough to get the small speeds that are found in coronal loops. So sort of 5 to 10 kilometers per second. That's on the edge of this. I think the phase speed propagation calculation needs to be improved before you can really begin to probe, so the smaller speeds you expect throughout the rest of the corona. But at least in the coronal holes where you expect flow speeds of say 10 to 50 kilometers per second in the low corona, then you can separate those reasonably well. So this is what the tool, the CoMP does. It goes through these basic steps and provides, reasonably basic outputs. It provides a number of outputs. Raoul will be demonstrating how this works. So we've got a virtual environment set up. He'll show you how to load it up, and nobody should need any software installed, basically. It's all done online. So you can all have a play around with it this afternoon and see how it works. And I will leave it there for any questions because I've reached the hour.
Questions?
I have a question that maybe is just stimulating later discussion, but are there fundamental differences in what the azimuths and the polarization is showing us compared to what this propagation has in terms of the way they're weighted, in terms of the way they're projected on the plane of the sky? Or does it all kind of wash out to effectively be the same thing, in which case they really are the same? So they can either help by reinforcing, or they can help by providing more information about out of plane of sky properties. I was just trying to think it through, and I'm not certain. I don't know if anybody has any comments on that. If they really are effectively doing the same thing. That polarization azimuth it's your plane of sky is defined by your observer, right? And you're still, if you have something which is like angled, which is not in the plane of the sky, but it has a projection onto the plane of the sky at an angle, would that be represented in exactly the same way in the azimuth as in the waves tracking, is what I'm wondering.
I think they're both projected the same way.
Yeah.
And in fact, that correlation plot a few back, Richard, if you want to go that, which the far
There are
right one there,
departures, right?
it's, I'm sorry.
The question is, are those departures noise, or are they actually indicating
Oh,
some?
I'm sure there's a lot of
effect?
noise and there's foreground, background, and various things. But that's the correlation, and that, the straight line is just a one-to-one. So they're very well correlated between the magnetic field direction, and there's uncertainty too. And you're taking arctangent of Stokes U or Stokes Q. These things are, and those fitting the line through those correlation plots in the wave stuff. I mean, there's uncertainties in these things, so sure there's some, but the correlation is impressive. I want to just also point out in the lower right there that there's a line that is a 90 degrees, and so that's the Van Vleck stuff in the lower right of that same plot. So.
Yeah, I'm just thinking there could be more information there. The one thing that comes to mind is that what you just said, one of them is the arctangent of the ratio of integrals, integral of Q along the line of sight divided by integral of U along the line of sight. Whereas the waves don't have that ratio built in. So there could be, the departures could tell you something about where things are in the line of sight, is what I'm wondering. So, because they are they are relative to slightly different mathematical formulations, and we might be able to explore that to our benefit.
I'll have to think about that.
Yeah.
Other questions? All right, let's thank Richard again.
Thank you.